Marden Lecture. Of course, we're thrilled to have Dr. Nagloo. In a moment, I'll ask Professor Kevin MacLeod to say a word about Maurice Marden, whose family has generously funded this lecture series, this ongoing annual lecture series. And then Professor Craig Gilboa will introduce our esteemed speaker, who we're very excited to have here. Before I do that, I just want to remind you all there's a reception afterwards in the math department in E495 in EMS. So please come and join us and say hello to the speaker.
So welcome to the Marden Lecture for 2023. It's a tradition for one of the senior members of the department to say a few words about Maurice Marden at the start of this, or before each lecture. It was announced to me at dinner last night that I am not only a, but the senior member of the department. And so this pleasant duty falls to me. I have to let you know that we have reached the stage where even the senior member of the department has essentially no personal memory of Maurice Marden and has to get his information from the department website, which I encourage you to do. There's a lot of interesting information up there, not just about Maurice, but about the history of the department in general. So Maurice Marden came to Milwaukee in 1930. If you know anything about the history of UWM, you know that UWM as an institution began in 1956 with the merger of two smaller two-year colleges. Maurice taught at the Milwaukee Extension Center, which was one of those colleges, for many years. Two-year college, undergraduate college. When UWM was formed, Maurice became, in 1957, the first chair of the mathematics department of the new four-year institution. He served as chair. He had two terms as chair, from 1957 to 59 and from 61 to 63. During the first of those, he lobbied and arranged for the mathematics department to get a master's degree. During the second of them, he lobbied and arranged for the math department to get a PhD degree. The mind boggles as to what we might be have here on campus if you served three terms. But neither of these seemingly were easy projects to accomplish. UWM had been formed in 1957, but it was still only one University of Wisconsin. You may think there's still only one University of Wisconsin, but in 1971, the current framework of the university, which is sort of 13 fiercely competitive and autonomous campuses, was formed. In 1957, UWM was still part of the University of Wisconsin. So Maurice had to go almost cap in hand to the mathematics department in Madison, to the graduate faculty in Madison, to the graduate school in Madison. There was no graduate school here at UWM, of course, because we didn't have a graduate program. And you had to get permission from all of these people to start and to establish either of these two programs. One gets the permission, the idea that permission was only reluctantly granted only if Maurice could guarantee that the programs here would be of the same high quality as the programs in Madison. He was able to convince them of that. Permission was granted, and so several years later, here we are on the campus of a research university in the southeast of Wisconsin. From all of that, you may get the impression that Maurice was a passionate research mathematician who pursued graduate work and research work, and he was. But he was passionate about all aspects of mathematics, including teaching, and particularly including undergraduate teaching. Before his death, he and his wife endowed the William and Maurice Marden Fund for the mathematics department, and that's used for two purposes. One is to fund a prize for the best undergraduate paper in mathematics in any given year. And the other one, which is why we're here today, is to fund the annual Marden Lecture. And the purpose of the Marden Lecture is to inspire, well, many purposes, but one of them is to inspire undergraduates to pursue further study of mathematics. So it's great to see some of our undergraduates here waiting to be inspired. It's a tough ask to do this, to talk about modern day research mathematics in a way that is understandable and will inspire undergraduates. But I've heard today's speaker talk, and I'm confident he's up to the task. So, thank you for being here, Ronnie, and I will ask Professor Gilbert to give a more formal introduction.
Thanks, Kevin. I'm Craig Gilbo. For those of you old-timers here, believe it or not, I'm the chair of the department now. So that's why this falls to me. So first I want to thank Jonah Gasker and also Pamela Harris, another young member of our department who did a lot of the work to make sure this happened. Unfortunately, Pamela is traveling right now, so she's not here, but thanks a lot, Jonah. So I'll get right to the task here. Ronnie, also, if you look up papers, sometimes Joel Nagloo, is from the island nation of Mauritius, which is off the east coast of Africa, a long way from Milwaukee. He's kind of gradually made his way here. He started out in graduate school in England with a master's degree at Imperial College in London, followed by a PhD at the University of Leeds under the direction of Anand Pillay. His next stop was City University of New York, where he spent several years on faculty and building an outstanding research record. Eventually he was lured away, and he's now an associate professor of mathematics just down the road from us at the University of Illinois, Chicago. As you can see, he's very young. I think he might be one of our youngest Marden speakers ever, but he's already accomplished an awful lot. For example, he is published in the Annals of Mathematics already. If you don't know what that means, that's one of the biggest accomplishments of a mathematician, if you can get a paper in the Annals, and Ronnie's already done that. If you're looking for a less technical paper, he's got a beautiful article that appeared just a couple years ago in the notices of the AMS. It's more expository to just kind of introduce you to the types of mathematics that he works on. And if you want to get started, I recommend you take a look at that article. It's really quite nice. It's also quite an honor to be invited to publish an article in the notices, because it's got to appeal to just about everybody across the mathematics spectrum. In addition to those things, and to kind of top it off, he was recently awarded a prestigious American Mathematical Society Centennial Research Fellowship. So he's got some nice years ahead of him with that funding from the AMS. So enjoy that. He gave a really great colloquium here at UWM yesterday, and so I'm really confident that we're going to have a lot of fun here today as well. And so I won't spend any more time. Let's get right to it. I'm honored to introduce Ronnie Nagloo to give the 2023 Marden Lecture. Let's begin by giving you a big Midwestern welcome.
Thanks everyone for being here. Thanks for the introduction, and for the organizers for the invitation to give this talk. And also thanks to the math department, who really welcomed me with great hospitality, and I'm really grateful for that. And I'm also really honored to be giving this year's Marden Lecture. And I hope you enjoy the kind of math that I've been looking at for the past 10 years. So, as the title suggests, we'll be looking here at equations that have a 120-year-old history. And so, my aim in this talk will be to sort of give an overview of the history of these equations. It turns out that they have appeared in a variety of important physical applications. I've named a few here, like statistical mechanics, random matrix theory, etc. However, the origin of these equations is not really by looking at physical phenomena and trying to model these phenomena using these equations. Rather, I'll spend some time explaining how they were discovered by two French mathematicians, Paul Painlevé and Bertrand Gambier. And then I'll go through some of the classical questions were asked in 1902 and that remained open for a long time. And then I'll finish with somehow more recent work, some of which I've been involved, where we've been able to really understand these equations algebraically. And so that's sort of the aim of the talk. So hopefully I do a good job introducing these equations that have fascinated me for a long time now. All right, so I'll have to take a few steps back since it's not clear to me whether everyone is aware of differential equations. So I'll do a leisure introduction to them and then slowly work towards trying to understand the Painlevé equations. So just to be sure we're on the same page and to fix the notation that I'll be using, first we will define the derivative of a function. And for me in my talk, all my functions will be with respect to time t. All right? And so here are some examples of functions we know and love. The world population at some time t, or somewhat a little bit more relevant nowadays is the number of people infected by some disease at time t. And so we usually like to visualize these functions by looking at their graph. All right? And for mathematicians, I know I'm being very vague about what kind of function, but that's done on purpose. And so for each time t0, we look at the value of the function and we graph the point t0 of 0 on the plane. And if we do that for all time t, we have this nice curve here. And you can think of, for example, here, the idea that I'm throwing the ball up in the air, and this function is measuring the height of that ball as it goes through time. I had a basketball analogy that I wanted to make, but I won't make it for obvious reasons, unfortunately. And what we are interested in is the rate at which these functions change. And so the derivative of a function f of t is a function that describes the rate of change of f with respect to time t. And my notation throughout for that derivative is d by dt, df by dt. And so if you've never seen that, I know most of you have seen it. So very quickly, if I increase the time t just by a tiny amount, I'd like to know, for example, if it's increasing, decreasing, but also how quickly it's increasing or decreasing. And so basically, I'm looking at the point, the tangent line, and I'm trying to figure out what the slope of that line is. And so the derivative of a function is a function that gives me this information at each point. Okay? And so feel free if you have any questions at any point to stop me, and I'm very happy to clarify if I'm not doing a great job explaining. Now, from the differential algebraic perspective, which is the perspective that I always take, we'll think that we have an operator d by dt, which take a function to a function, if I apply the operator, and what function it'll send is simply send it to the derivative of that function. In other words, if I apply that operator to the function f, I get its derivative. So I've written down here some of the properties of that operator. This is mainly for those who, I'll talk about some solutions later on, I'll talk about some equation, a transformation. For those who want to see whether I'm lying or I'm really being straight, these properties here will help you check what's going on. Okay? And so this derivative is linear, so if you take a sum of function and you apply the operator, you get a sum of the operator applied to the function. If you have a number and you apply the function, the operator, you get 0. And more generally in this talk, by a constant, I'll mean a value or a function, which when I apply the operator, I get 0. So usually they are numbers, but it can happen that they are more general than numbers. And again, so this is simply a technical little property. If you have a constant times or a number times the function and you apply the derivation, it's simply linear in that too. So it's the constant times the derivation. Okay? So these are useful for when you'll see some of the equations later, some of the transformations and so. And one notation that I'll have to use later on is, now that I have this operator, it's very easy to think of what the d squared of f by d2 square is without even having to think about what it means in terms of rate of change. It's simply I apply the operator twice to the function. Okay? All right, so now we've set up. And so what I want to do is I want to introduce what a differential equation is by looking at a particular instance of a real-life problem, and then show how the differential equation appears. Now this is going to be important because later on I'm going to argue that the Painlevé equations did not come this way. Okay? All right. So let's use something that's quite relevant. So if we consider IC19 of t, which is the number of COVID-19 infected people at time t, well, we know now that it's really important to know how that function changed with time. Okay? And it's critical, it was critical indeed to sort of have a hold on this number, right? And so suppose A is the number of people that's being infected per unit time by every single spreader, and B is the number of people recovering at the same time. So the number K, which is the difference between the two, captures the infectiousness of the disease. And so the change in the number of people per time equals that number K times the number of people who've already been infected. Now this is the simplest model of that. I'm not claiming that it's 2 points, that's what people are using. But what they say is that the derivative of that function is that constant times the function. And so what we say is that the function IC19 is a solution to the differential equation dy by dt equals ky. Okay? So a differential equation, that's not a definition, but you can think of it as an equation that not only expresses things algebraically about an unknown function, but it also involves the derivative of that function. Okay? And now this is always my favorite slide to show if you've never seen the differential equations before. So these are the Painlevé equations. So quite a lot to look at here, except for the first one, which are really simple to look at. The others, even I've worked with them for so long, I haven't really memorized all of them. So they are differential equations, as you see, and it involves both algebraic expression in this unknown function y, but also the derivative of the derivative of that unknown function. Okay? And some of them also have the derivative of the function itself. Notice that except for the first one, all the others have these values alpha, beta, gamma, delta, which are numbers. And so really, the P2, for example, it's not only one equation for each value. So you have P half, which is one equation, P prime, a different equation. And so really, these are the families of differential equations. Now, every time I give a talk and I put this equation on the slides, people ask me whether there's a way to kind of guess for the simple one what kind of physical phenomenon is going on behind. And the point is, there is not, right? And the history of how they came to be will explain that, okay? But then, of course, they do, in the end, appear as equations involved in real-life problems, but we won't look at that particular aspect of the theory, okay? All right, so now I want to take a step back and explain how did we, or did Painlevé and a student discover these equations. So, before doing that, let me just mention that at the time, this was not necessarily the way differential equation appeared in the literature. So, differential equation, of course, first came into existence by the invention, with the invention of calculus. So this is the page, a photo from a famous book of Isaac Newton, where the notation for a small change in first infinitesimal is somehow first introduced. But for us, what really matters is that by the end of the 19th century, differential equations were already everywhere in mathematics. Okay? They even appeared in theoretical fields such as number theory, so not just in mechanics or things like that. And in all those cases, they appear as equation that naturally is describing the mathematical or real-life problem you're trying to work with. Okay? But that is not how Paul Painlevé thought about these equations. Now, Paul Painlevé was a French mathematician. He not only did work on the Painlevé equation, he worked with differential equations in many different contexts. But at some point, he got interested in that question about the Painlevé property. But before I say more about the kind of problem he's interested in, let me mention that he's a very interesting mathematician. He indeed served twice as the Prime Minister of France and was also the Minister of War in 1920. So there's a nice square in Paris dedicated to his memory. So very interesting mathematician, and I think at that point in his career, he didn't really think about math anymore. So he had to sort of move on from those activities. But here's the kind of problem that he had in math. So find, if possible, all differential equations that have nice solution. Okay? So the all here is already an impossible thing to do, but the question he really was sort of thinking about was about nice solutions. What does that even mean? So, okay, this is where those properties that I've introduced before will be useful if you want to figure out these things. So this is the equation we had before, and we know that IC19 was a solution. But it turns out that that's not the only solution. For any constant c, any number c, c times that function is also a solution to the equation. So the difference with algebraic equation is that in one variable is that differential equations usually have infinitely many solutions. Okay? Another thing that is very important with differential equations is that once you solve them, usually you have a constant of integration or more constant of integrations that appear in that solution. So this is an easy example. Here's a different one. That's a Riccardi equation. So dy by dt is minus y squared. And so what's the solution in this case? The solution is y over 1 equals 1 over t minus c. So this time, the constant of integration appear in the denominator of the function. And here's the last one. So this is dy by dt equals negative half y cubed. And it's not difficult to work out that in this case, the solution is 1 over the square root of t minus c. Okay? So again, the constant of integration appears at the denominator here. But of course, division by 0 is undefined. I don't have to argue that. And so time t equals c is what we call a problematic point, or singularity, in the last two equations. Okay? So we have singularities of the solution. However, the c are not fixed, right? So for each solution, we have a different singularity. Okay? And so we say that the problematic point is movable. Now, mathematicians are clever, and for a long time it was known that the kind of solutions that is simply the reciprocal of a nice function that has zeros, it's not very difficult to deal with. However, the square root of t causes a lot of trouble when it comes to studying this solution. Okay? And so, what is the Painlevé property? A differential equation is said to have the Painlevé property if the only movable problematic points are of the first kind. So for mathematicians, or for those who know a bit more complex analysis, here we're talking about poles. And so Painlevé property are those differential equations that have nice solutions. And so what was Painlevé's program? Well, to find all the differential equations of this very special form that have the Painlevé property. Okay, so here, this is f is a rational function in 3 variables, but it's a function of y and dy by dt and t. Okay. Now, just to note that the problem of doing the same thing when you only have y and y prime had already been solved because it comes from a very nice problem involved looking at curves. And so that was what Painlevé was after. And so here's a photo of his 1902 paper where he posed that problem again, but in French. I've already translated it. And so what he found is that every such equation can be transformed into one coming from only 50 equations. So having this Painlevé property is it's a very strong assumption on the solutions. Now, with the help of his student, Bertrand Gambier, he found out that 44 of those can be solved in terms of previously known functions. Okay? And there were just 6 equations. So he needed the help of his student in the sense that when he initially worked on them, he found that there was only 2 left and missed out on 4. And then his student noticed that there was some mistake in calculations. But what was somehow funny in that story is that independently of Painlevé and Gambier, Richard Fuchs had already discovered the 6th equation, and in similar work, Painlevé himself had discovered the Painlevé 6, but then forgot that it had to be among those 6. So it's of course, it's very difficult to deal with one equation, and so now I can again put back this list of equations, and now I hope they are less mysterious in the sense that these are the 6 equations that couldn't be solved by already known functions, such as the exponential function, sine function, cosine function, etc., but have this property of having nice solution, satisfying the Painlevé property. Okay? Any questions about that? All right, so now that we have this equation, it makes sense to then try to understand a little bit more about the nature of the function. Okay, so the reason why this was important is, as we've already said, they will appear, now we know that they appear in important physical applications. And so there had been for a long time this question hanging around, how do we deal with this equation? Okay, so I want to say a little bit about that. But before I do so, let me point to a quote of Henri Poincaré, who was back then a leading figure in mathematics. And he says, les mathématiques constituent un continent solidement agencé, dont tous les pays sont bien reliés les uns aux autres. L'œuvre de Painlevé est une île originale et splendide dans l'océan voisin. So I've written a very quick translation there, that although the work is interesting, well, it's a sideshow. But what I like about the quote is that it's an island, original island in some tiny ocean, in some ocean, and that reminds me of my own island, and I worked with the Painlevé equation, so I like it there. And so, of course, nowadays, I've already mentioned that they are no longer a sideshow. For example, a quick search with just Painlevé in the title gives you so many publications, recent publications. And I mentioned that they appear in physical application. I just wanted to give one that, for example, in 1964, a paper of Toback and Peterson showed that the tumbling motion of bodies entering the planetary atmosphere, some of the aspect of this theory is governed by the equation of Painlevé. Okay? And to me, what's important here is the date 1964. Why is that? Well, not only did Painlevé discover this equation, he made some bold claims about that, right? So he said, and we've already seen that these equations are new, right? They cannot be solved by functions that we already know. And he also mentioned that they were highly transcendental. So let's focus for a few minutes on the new function. Well, as I said, we've seen that fact that this equation cannot be solved in terms of previously known function. However, Painlevé knew that his proof was based on work that had a major gap. And so his hope was that one could resolve these problems in the near future. Unfortunately, to this day, this gap still hasn't been fixed in that theory. And so the reason I mention that is that in 1964, when all these equations slowly started appearing in physical applications, people didn't know whether they should continue trying to solve them using known function, or they should give up that enterprise entirely. And so it took 19 years, but now we know exactly when the solutions to the Painlevé equations are new functions. Okay, so Keiji Nishioka, a Japanese mathematician, inspired by some work of Ellis Colchin, who was the founder of differential algebra, gave a complete proof of that assertion, that the solution of the first Painlevé equation is indeed true new function. And so the key idea here is that answering the question naturally sits in the realm of differential algebra. Okay? And following this, a strategy that emerged very quickly, and works of Hiroshi Umemura and Umihiko Watanabe using differential algebra completely resolve this question for the other equations. Now, this tiny sentence here really doesn't do justice to the work of Umemura and Watanabe. So it spans over about 10 years, and as we've seen, these equations are really complicated. However, to talk about their work is really technical, and I would spend more time talking about that than other things. So don't take this as just saying, oh, Nishoka found it, and it just then follow through. It is really deep and difficult work. And so yes, so now there's no ambiguity. So whenever the Painlevé equation appears in applications or appears in mathematical problems, people know that they don't have to try and solve them using known functions. Okay, so that method is not going to work. So they are really true new functions. And also I want to mention that thinking about it now, we've sort of a little bit, as time has passed, it's no surprise that these equations will continue to appear in problems as we move on with time. The point is that they have the nice solutions. So they are those functions that can possibly describe more and more complex problems as we move in time. Okay? All right, so now I want to talk about how I personally got into this story, and that's about the other part of the claim of Painlevé, which is that these functions are also highly transcendental. Okay? So let me try and explain what I mean by highly transcendental by first asking a different question. What makes a function special? Okay? Well, there's no definition of a special function, but we all know and love some of them. So, okay, maybe if there's an undergrad student who doesn't really like mathematics, maybe that's not something they really like. But there's a trigonometric function, the exponential function, and the logarithmic function, right? But just like the Painlevé equations, when they were discovered, they were new functions. So here, for those who know, they are transcendental, true transcendental function. They each satisfy a differential equation, and they appear themselves in physical application and even other problems in mathematics. So in that sense, they are very similar to the Painlevé equation. Okay? So, but does that fully characterize the nature of these functions? Well, we know that the other special functions satisfy nice trigonometric identities for the sine and cosine. So here, that one is explicitly saying what it's saying. The second one is saying that sine of 2t as a function can be written algebraically in terms of sine of t and cos of t. We know the same story for the exponential identities. For example, e to the 2t, the function can be written as e to the t to the square. And there's nothing special about 2. We can do the same for any m. And similarly, we have the logarithmic identities, right? So the function L to the 2t can be written in terms of the function L to the t plus some constant, and the function L to the t squared can be written 2 times L to the t. Okay? and that there's nothing special with 2, so it works with any m natural number. Okay. All right, so I hope you see where I'm going with that. So it follows that sine t, cos t, sine 2t, cos 2t, and 3t satisfy the same differential equation. Now that might be slightly less known because we know differential equation for sine of t and cos of t, but there is a differential equation, the uniformizing differential equation, that they all satisfy. And so what we're saying here is the solutions of that differential equation satisfy these algebraic identities. Similarly, for the exponential function, they satisfy all of them the same differential equation, and these solutions have identities between them. And the same story with the logarithmic function. Okay? And so one can guess what highly transcendental means now. So Painlevé also claimed that the solutions of the Painlevé equation cannot have any such nice algebraic identities between them. Okay? And so that's the meaning of highly transcendental. Now, there was no proof for a long time, but everyone believed it. And the reason is these identities allow us to study these differential equations very efficiently. So you know that there's some algebraic relations among the solutions. All you have to do is pick one, and then you can generate all the others from there. And so mathematicians have tried with the Painlevé equation, and then gave up, because you couldn't really find. And so what my first contribution to those work came in 2014 and 2020 was to give a full proof of that claim of Painlevé, that these functions are really indeed highly transcendental. I'm going to state the actual theorem, give a statement in a moment, but let me just first mention that Nishioka himself in 2014 had already proved this result for the first Painlevé equation. And much as his earlier work on proving that these functions were new, he used a lot of differential algebra and also had a lot of computations involving differential algebra. But as we know, the first Painlevé equation is somehow very simple. And so very simply, much simpler to deal with. And we've tried, but his computation really doesn't work beyond the first Painlevé equation. So my work, including the one, and I apologize, I forgot to mention that the first one, so I should go back, is joint with my advisor, Paul Painlevé. We somehow use model theory, which is a branch of mathematical logic, but combined with differential algebra to approach this problem. Okay? And so here's a statement of what we want to say. If you give me n distinct solution of one of the Painlevé equation, here I say with generic parameters. So I won't give a definition, but just think like if you pick an equation at random. Then what you have is that the 2n function y prime here, should maybe write this down, sorry. Y prime here is d by dt of y. Then these 2n functions are algebraically independent, meaning that you will not find none of these algebraic identities between them. Okay? And again, let me just say that model theory allows you to give a proof technique that works for all these equations. So you really don't even have to worry about the form of the equation, and you are able to show that it's really not possible for such algebraic identities to exist. And unfortunately, that's of course very technical, and I cannot go through it here. And so this was the answer to that question about the transcendent, whether these functions are highly transcendental. Now, of course, this tells to anyone who sees these equations that they should never try to use the technique of finding identities to deal with them. That's out of the question. But one may wonder, it seems negative, we say that there's no algebraic identities, but it also can be useful to answer further questions. Okay? And so I want to talk about the story of the Bertrand transformations. This is again another method that allows mathematicians or physicists or anyone who have to deal with the equation to somehow simplify the way you look at them. So for simplicity, I zoom here on the second Painlevé equation, but everything I'll say holds for the other equations. Okay? So what we showed in the previous result was that if you give me solutions of the second Painlevé equation, let's say with parameter pi, then they don't share any algebraic identities between them. But one can ask a different question. What if I take a solution of P2 at pi, chosen at random, and a solution of Z of P2 at pi plus 1? Right? Could there be an algebraic identity, an algebraic relation between Y and Z? Okay, so the question, more general question is, suppose you have two parameters, alpha 1 and alpha 2, which are distinct. Could there be algebraic identities between the two solutions? Right? It turns out that for the Painlevé equations, this is yes, there can be. Okay? So for P2, let me introduce the Bertrand transformation. So if I give you Y a solution to the Painlevé equation, so as you can see, I've started to talk about Y as solution. That's how, as a differential algebraist, you do. You just think of it as a point. Any one of you can just think of it as a function, right, that satisfies this equation. Now, if you are sort of, you know well your complex analysis, think of a meromorphic function that satisfies this equation. Then what you have is very easy to check. Again, these properties I showed earlier, you'll check it in no time, that if you take minus y and you plug it in the equation, minus y will then satisfy the equation P2 with negative alpha. It's not very difficult to see. So there is an algebraic identity between that solution, oh, that should be a y, I apologize, sy and y. That's a really easy identity. Here's a slightly more difficult one, but it's again very easy to check, that if y is the solution and you plug in this function in the Painlevé equation, you'll see that you'll get a solution of P2 alpha plus 1. And you can trust me on it, but you can also check it. And here's the last one. Oh, that should be a minus. Don't know how typos put there. If you plug in this time this variation of the function into the equation, you'll get a solution of P2 alpha minus 1. And so what this is saying is that when you look at fixed n alpha and you look at P2 alpha plus or minus n, where n is a natural number, you will have algebraic identities between them. Now, the way I get from P2 plus 1 to plus n is I apply this several times, okay? And so somehow it looks like slightly more delicate questions, right? So we cannot simply say that for any two parameters, there won't be any algebraic identities. However, given that we know so much about the solutions within their own confines, so as the solution to one equation, we can use that to somehow deduce more. And so the last kind of result I want to talk about is based on that. So the old belief again was that the background transformations are the only such algebraic identities. Okay, so however, the reason why this is not an old belief, because that's what people do when they have a differential equation. They want to try to figure out whether I can get from one equation to the other and try to see whether there's a transformation. People couldn't find it, but you could never say there's no, because you need a proof of it. And so a more recent work, we've joined with my collaborator James Freitag, was to answer that question positively. So suppose you have two parameters that are distinct general constants. So again, pick these two at random, go this way. If there is an algebraic identity between the solutions of P2 alpha plus 1 and the solution of P2 alpha, P2 alpha 1 and P2 alpha 2, then it must be that alpha 1 minus alpha 2 is an integer, okay? And that this algebraic identity comes from the background transformation, okay? So somehow the transcendental nature of this equation does not allow room for many ways to get from one equation to the other. If there was one natural way that it happened, which of these background transformations are, then that's the only way you can do so. And just to say that the way we prove this is when I was working with a single equation, I already was wondering whether you could go from one equation to a different one. So could you find a transformation that goes from P2 alpha, say, and P3 alpha being that? So could solutions of these two different equations be algebraically dependent? And so it turns out that, again, the same general methods that we used to show that the Painlevé equation is highly transcendental can be used to show that even in those cases, you would never find background transformation between these equations. And so, in a way, we have a very good picture of the Painlevé equation, right? So we know that there are new functions. We know that among them, if I take one equation and I look at the solutions, there are no algebraic identities between them. And if we take two equations, there can only be those background transformations between them. So, did we answer all those questions about them? Well, it turns out that everywhere I've used the term general constant. Okay? So everywhere what we were looking for is a general phenomenon of transformation. So these background transformations are defined for the whole equation for every alpha. And so what we show here is that for every alpha, there couldn't be an algebraic identity. What we aren't able to do, even for the highly transcendental question, is if you tell me, what about instead of p2 pi, what about p2 at parameter 1? Right? Are these functions highly transcendental? Well, we don't know yet. So this is still open, and that method where you can take a general constant and fully answer that won't work. It really depends on that. Same for, what about if I take p2 with parameter 1 and p2 with parameter square root of 2? Could there be an algebraic relations between those? Could there be a background transformation? Well, again, we don't know, because we haven't taken it in a sort of random fashion, right, in a generic fashion. And there again, these techniques where we use general constant does not work. So to really finish this whole Painlevé story, which was started about 120 years ago, the hard problem now is to try and look at those specific parameters and try to see whether among them or between them there are such transformation. And so work is on the way. We have partial results. However, we are still a long way to go. And so this is where I want to end my talk.
Sure, yeah. Are there any questions for our speaker? I have a question. Can you say more about the definition of general or generic in your constant?
Sure. So yeah. Okay. So for example, let me take examples. So because somehow it depends on which problem. So for the problem of highly transcendental, when you look at let's say a Painlevé equation that has alpha, beta, gamma, delta, and you want to ask whether the solutions have an algebraic dependency, you want that the constants are algebraically independent over Q. Okay? So, for example, P4 has a parameter, 2 parameters. So if I were to put E and pi here, I couldn't tell you yet, because we don't know whether E and pi are algebraically independent. Okay? For the problem of a 2 equation, and I can just go for P2, do we have an answer for something that looks like, let's say, right? So pi and square root of pi are not algebraically independent. Only one of them is. Yes, still we can show that between the two, you cannot have an algebraic relation. So the problem of pairs of equation does not require that the constants are both algebraically independent, but for the question of fixing one equation, this one you need that the constants are algebraically independent. And I didn't want to write some more on the slides, but some of you might say, what about if I take 5 equations, right? All 5 equations together. Could there be identities between solutions of the 5? It turns out, especially for those who were here at my talk yesterday, we've shown that it only can arise by pair of solutions. So if you were to find an algebraic identity with 5, that's because you found one between 2 solutions. So at least we've reduced the problem to just looking at 2 equations.
Well, if there are more questions, then come to the reception and ask there. So let's thank our speaker again.